So it was funny. Manat was here last week, and she was visiting. Um, uh, and it sounds like she's being very successful at Mac, which is great. I'm glad to hear it. And I've been in touch with a bunch of our students at various places this year. And do you know, like, Eastdale doesn't send a ton of kids off to post-secondary, but we've been sending kids off to science post-secondary at like a bigger clip than just about everything else combined in the last like 5 or 6 years. We've really been pumping kids into science, bless you, which I'm very proud of. But what's equally encouraging is they've been doing really well. The one advantage of going to a small school like this, maybe you've noticed over the last couple of years that we have university students popping in and asking for help, and I edit papers, and Elastic edits papers, and we help with assignments, which is something that's available to you here that probably isn't available if you go to a bigger school, right? That's one of the things we're able to do here that you just can't do if you teach 500 kids in senior science, right? But anyway, Manat was saying that she has one professor in chemistry who she can't understand, and he doesn't speak very clearly and goes very quickly. So she's been rewatching all of my lessons. But she said the first one she logged into was a lesson from this year with you guys of something they're doing there. And the first thing I said was, all right, let's get going. And to anyone watching online, do something better with your life. Apparently I said something like that. And like literally the first thing in the live stream was me making fun. So Manat, if you're watching this one, this is my atonement. I'm sorry for telling you to get a life, nerd. Anyway, so we're going to talk about oxidation reactions. And oxidation reactions can have lots of definitions. We're going to work with a sort of simplified definition of that for the purpose of this unit, where we're going to define oxidation as meaning reactions that result in more bonds to oxygen. It doesn't necessarily have to mean more oxygen. It may mean that, but it's going to mean more bonds to oxygen. So that could be adding an oxygen, absolutely. But what's the other way you could be making more bonds to oxygen? You could add a new oxygen to the chain, or double bond. Good. Or it could be forming a pi bond to an existing O. That's going to be our sort of working definition of oxidation for the purpose of this unit, for the purpose of this lesson. That is actually a fairly narrow definition. Oxidation is actually a really big category of reactions. Like I said, when we get to our 5th unit, you'll get a better definition of an oxidation reaction. If you've taken 4U Bio and you remember 4U Bio, you've seen a more sophisticated definition of oxidation. But for now, this is going to be our working definition. And it's a good one. It's effective for what we're doing here. What functional groups have oxygen in them that we've learned about so far? Aldehydes, ketones, and alcohols. So really, we're talking about, from what we know, and we're missing one, of course, carboxylic acids. So we're talking about reactions that are going to, in some way or other, involve aldehydes, ketones, carboxylic acids. Does that feel fair? Okay, we're going to start with oxidation of tertiary alcohols. So for the purpose of what we're doing here, we're not defining oxidation reactions as ones where the first oxygen gets put on. In fact, where the first one gets put on, that would fall under the category of either addition or substitution, right? Right? So we had addition reactions that resulted in an alcohol, right? We said if you take, say, propene or some other ene, some other chain that has a double bond, and react it with water under the right conditions, you can get an alcohol, propan-2-ol, right? We also had substitution reactions, where we said if you... we actually didn't do a substitution that gave us an alcohol. That's not true. There are substitutions that give you alcohols. But here we're going to talk about working with something that already has oxygen present and increasing the number of bonds to oxygen. Does that make sense? And I decided, this is a new way to approach it. I decided to start with an example that doesn't work, and we'll talk about why it doesn't work. So you can't oxidize a tertiary alcohol. And we'll talk about what that looks like. Now, any oxidation you do requires an oxidizing agent. These are compounds that can lend oxygens to your chain in intermediate steps. Look at me. Organic reactions always happen in multiple steps. In this course, we're not going to learn any of them step by step. Some of them take several steps. We're always just going to learn what you start with, what you end with. All right? But in reality, organic reactions tend to happen in stages. First this happens, then that happens, then that happens, then that happens. When you get to university organic chemistry, you'll be expected to know the steps along the way, which is more work, but it also makes it clearer and makes more sense why some things happen and others don't happen. So in this class, things can be a little hand-wavy, and we just sort of say this happens. When you go deeper with it in future years, you'll learn the specifics of why reactions happen. You'll also learn why people develop drinking habits. But anyway, organic chemistry, she's tricky. She's a challenging one. So I want to look at a tertiary alcohol. What's a tertiary alcohol? Very good. What's the simplest tertiary alcohol? What's the simplest alcohol I could make where the alcohol's on a carbon that also has a branch? We could go one better than butane. We could go propane, right? Because prop is 3. So you're right, butyl would work, but we can do propanol where the alcohol is on carbon 2. But where we also have a branch on carbon 2. So a methyl propanol. And I'm going to draw the hydrogens. We would never, like going forward, you'll always just draw skeleton diagrams. But I think when you're learning, it's helpful to really see it as a full structure. And if we try to oxidize this, we're going to get no reaction. And that may seem like a weird place to start, but I want to talk about why. And maybe that'll help make sense of how the other ones will work. Now, to try to make an oxidation reaction happen, we need to add an oxidizing agent, which sometimes will be shown just like this. That's a symbol that can mean oxidizing agent. Oh, sorry. Like this. Oxidizing agent. But more often, we'll actually write the specific one we're using. And the two most common ones are potassium permanganate. That's a strong oxidizing agent that we use quite frequently. Or potassium dichromate. So I want you to be on the lookout for these particular things because these are the most common oxidizing agents. In our chemical storage, we have to have a shelf that is just for oxidizing agents. The reason for that being that because they tend to oxidize things, they tend to be very reactive. Just about anything can be oxidized, so they need to be kept by themselves so that they don't, if there were a spill or if something did get knocked over, they wouldn't catalyze other reactions to start happening. Does that make sense? So we have a shelf full of oxidizing agents, and on that shelf we have potassium permanganate, KMNO4, which is this beautiful rich purple color. Some years in grade 11 in chemistry, I do a lab with it, and some years in grade 12 chemistry, I do a lab with it. So I don't think you guys have seen it. And then we have another one called potassium dichromate, K2CR207. We actually don't have any of that right now, but these are kind of the two most common oxidizing agents. They are not the only ones. All right, manganese dioxide is another one. There's plenty of other oxidizing agents, but these are the two that you will see over and over again. And in an organic lab, potassium permanganate is quite common. And then the other thing we tend to do when we are trying to oxidize is we heat. We add heat. We heat. Now, there's no reaction here. And we'll put a little note there. A tertiary alcohol cannot be oxidized. And the reason a tertiary alcohol can't be oxidized, I want you to tell me. Look at the structure, because our definition of an oxidation reaction is that it's a reaction that results in more bonds to oxygen. So the chain is going to be making more bonds to oxygen than it currently is. In this structure right now, how many bonds to oxygen is the chain making?
One.
Just one. Carbon to oxygen, right? And then the oxygen's making a bond to the hydrogen, but that's not considered part of the chain. The carbons are the chain, right? So in our chain right now, this bond here is the only bond to an oxygen, right? So the two ways that we could make more bonds to oxygen here is we could add an OH to this, or we could add a double bond O to it, or we could turn this into a double bond, in which case that H would have to be released, right? Those are the ways available to us, right? We could add another oxygen to the chain, which is either going to be an OH or a double bond O, right? Or we could form a pi bond. That would be where a bond to OH becomes a double bond to O, right? Why can neither of those things happen at this spot on the chain?
Because there's already 4 bonds being made.
Yeah, because there's one bond already being made to oxygen, and then the 3 other bonds are the bonds of the chain itself. And this is not a reaction that will cleave the chain. There are some reactions that break a chain apart. Oxidation reactions don't do that. So the reason is a tertiary alcohol cannot be oxidized because the carbon involved has no free bonds to break. And by that I just mean no bonds to H. In other words, if we tried to break one of carbon's existing bonds to make another bond to oxygen, it would break the chain apart. And that's not going to happen in an oxidation reaction, right? If we wanted to turn this into a double bond, what bond breaks? Maybe that one? Well, that would break the chain. Maybe this one? Well, that would break the chain. So you can't do it because you would have to take apart 2 carbons. And that carbon-carbon bond is very stable. That carbon-carbon bond is very, very, very stable. They are very hard to break. Does that make sense? Yeah.
Does it not count to add like an oxygen because we're at the end of the chain or something?
That would be an addition or a substitution, depending on what you're doing. In this case, it would be an addition. So you could do it, but it wouldn't be an oxidation reaction. So an oxidation reaction is making more bonds to oxygen where at least one already exists. So that is possible, but it would be a different type of reaction. Good question. Any other questions? Is that up? Down?
Yeah.
Can I scroll this way? Is that what you want? Yes. So again, any questions about that? By contrast, we'll look at what happens when you can do one of these reactions. In the next example, we'll do a secondary alcohol. And again, what's the simplest secondary alcohol? It's going to be a prop again. Propan-2-ol, this time with no chain, right? With no branch. So what was this one called? I guess I should put the name of the compound here. What is the name of this compound? Okay, it's propan-2-ol, but there's one more element to it we're missing. What about this? Yeah, 2-methyl. It is such a good feeling when you just eyeball where to start writing and it lines up so it looks like it was always there. You know what I mean? Sometimes I actually try to work backwards. So I'll have it like propan-2-ol, and I'll say like... But it's surprisingly difficult to spell a word backwards. Or at least I find it quite difficult to write a word backwards. It's like in teaching math. I learned to be very good, or not very good, but I learned to be at least passable at like writing numbers upside down, so that I could like stand across, like sit across from a kid and like look at them and talk to them, but then like write on their page. That took me like 10 years to get decent at. I'm still not great, but I still do little kid numbers sometimes where you're like, oh God, is that a 3? Or is that a 3 backwards? Anyway, that's a 3.
Do you think if you had to take a program in the University of Chemistry that you would like pass all the exams?
I think I would certainly get... I'm not going to say I would never make a mistake. If I took a first-year chemistry class, I'm very confident my mark would round to 100. like just I've been teaching this stuff. First year chemistry is basically just high school chemistry again with like 5 new topics put in, and I remember all that stuff. And I've been helping so many kids in first year chemistry over the last 6 years. I'm very confident I get perfect in a first year chem class. I'm confident I get perfect in a first year bio or physics. I'm basically confident I could do first year university again and get 100%. Second year, I'm very confident now that if I took an appropriate leveled university science class, like I keep taking science classes at university because I'm curious and I want to learn more. And I've gotten between 95 and 100 on every one I've taken as an adult because it's different. I have the background. I don't have to take 5 classes at once. And I've learned how to be a student, you know? So that was not what my grades were like when I was in university, and those grades mattered, unfortunately. But like, yeah, now every time I go to university and take a class, I'm typically aiming for 100. But it's easier because, again, I'm not doing 5.
What about organic chemistry?
I retook organic chemistry and got a 95. I only took it through second year. So I really at one point would love to go back and actually learn some advanced organic chemistry. Like Alastrek has a much better education in chemistry than I do. Like he actually did his honors thesis in like an organic chemistry lab, and he's the real deal. I'm a big fake. But I know high school chemistry very well. And in the end, that's my job, right? And to be clear, teaching is like being a parent. I think of you guys as like my kids, which is why I'm so mean to you, because I think it's important to be mean to your kids. But I also think like your goal as a parent is that your kids will like surpass you, right? So it's nice. Kyla Cron sent me a paper to edit a couple of weeks ago, and I was able to edit like her grammar and like some of her thinking, but like she's in 3rd year now and I don't know all the stuff she said. Like it was a biology paper, like it was a human physiology paper about like blood, and like some of the stuff I knew and was familiar with, and some I was like, oh, I'm assuming that's true. I don't have time to look it up and check all your references. So, you know, like the goal is you want your kids to go off and be smarter and more capable than I am. And some of you are already much smarter and more capable than I am. And the rest of you will get you there. I was thinking you, but okay, her too. I mean, really most of you. I'm a big dummy. You can do a lot better than me. But honestly, like, let me tell you something else. It's not the smartest kids who get high 90s in university, nor is it the dumbest, right? Like, you do have to have a certain level of natural intelligence, obviously. Like anything else in life, you have to have the gifts, right? I could work my tail off till the day I die, and I'm never going to be an elite basketball player, an elite volleyball player, or an elite musician. I just don't have the skills, right? But I just do not have the raw natural talent. I did have the raw natural talent to be a student. What I then learned was that if you have the raw natural talent, you can be a 70s or 80s or 90s student, whatever. But if you want to be a 90s student, you want to be a serious student, you got to put the work in. Like that's the people who do well. You got to have good habits, which I learned too late. I got to first year. This is the danger in science. First year is a lot of review. And so if you learned your high school science well, and if you can cope with the workload, because first year comes at you faster, but the material itself is not actually really any heavier than high school in science. I'm sure different disciplines are different, but in science, first year, it's the workload that kills you. Second year, it's the content that kills you. My problem was our high school science program was so hardcore. Eden at the time, they really thought they were running some kind of elite preparatory school. They were so hardcore. Like their late policy was just 0. If it was late, it was 0. Like they made us buy lab insurance. You had to pay for all of your broken glassware, or you could pay for insurance so that if you broke glassware, you didn't have to. If you didn't have your homework done, you had to stay on that lunch and like clean glassware and like scrub the sinks out. Like, they were just hardcore. So we got to university, and my first year at university, I did great. I got like 90s in all my science classes, but I took the wrong message away. I took that to mean, oh my God, look how smart I am, right? I was like, I am so smart. Look at all these people struggling and I'm doing great. I am so smart. And you want to know something? That was the wrong message. What I should have said was, wow, I was better prepared than some of these poor souls who had like laxer teachers. And so I came here with an advantage. But in fact, I learned exactly the wrong lesson. Started skipping class, started this or that. And then second year came and I got just wiped out. And all these kids who I'd scored like 10% higher than in first year, their egos kicked in. They came back with a vengeance. Now they were all getting 90s. In my second year, I was getting like 50s and 60s. I was a train wreck. Because in the end, it's your work habits that are going to get you there. Nobody cares how smart you are. Nobody cares how smart you are. It's a useless skill unless you're also hardworking and focused, right? Like, what good is a smart, lazy person? No good. They're useless. They're not good for anything. In fact, they're worse than it's annoying, right? Like, yeah. Anyway, enough about that. Let's look at a secondary alcohol. We said that propan-2-ol is the simplest secondary alcohol. So let's look at that. Carbon, carbon, carbon. Hydrogens all around. All right. And then we said an oxidizing agent. Somebody give me an example of an oxidizing agent. KMNO4. What's KMNO4 called? Nice simple organic compound. K is potassium. MNO4 is what ion? MNO3 is manganate. Or MNO3 is manganate, rather. So if you remember your naming conventions from grade 11 chemistry, that would make MNO4 the version with one extra oxygen. Permanganate. Good. If you don't remember that, that doesn't matter. You're not actually going to worry about any of that physical chemistry this semester. But if you do remember it, that's good. That'll serve you well. Wow, this really doesn't want to erase. I'm glad I wrote it. Guys, I'm sad right now. Hello. Okay, so we said... Sorry? Are you all done?
No, I'm trying. I don't.
Bring it in. You can show me.
I don't know with the Lewis for Lewis. I don't know the letters for the chemicals.
Oh, there's periodic table in the handout folder. Like the period 1 handout folder. There's periodic table right at the front. Okay, we said we're going to make more bonds to oxygen. And if we're going to make more bonds to oxygen, where's that going to happen? Yeah, we've got a sigma bond here, and that's going to get added to it a pi bond, which means some things are going to have to be displaced because there's the pi bond right there, right? That bond is going to, right now it's a sigma bond, but it's going to become a pi bond, right? Which means what's going to get displaced? Yeah. Both those hydrogens are going to have to get displaced. And what we would end up with is... Very good. What we end up with is what? A ketone. When we oxidize a secondary alcohol, we form a ketone. And what would this be called? But what else do we have to get? No, you'd think so. But remember, this is going to be happening in solution, right? Because if there's KMNO4 there, this is in aqueous solution. So what this is telling us is in an aqueous solution, of KMNO4, which is an oxidizing agent, right? And it is a perfectly reasonable assumption to think that you're going to get hydrogen gas, but we actually don't. And the reason we don't is because carbon keeps that extra electron. It keeps hydrogen's electron. Oxygen keeps that electron, right? Which means those hydrogens leave without their electrons, which means we get, we get H plus ions. Yeah, totally fine. And this means that the solution will become what? Very good. The solution becomes acidic. Yes. Oh, it shouldn't say propan-2-ol. What should it say? Not an aldehyde. If it's an aldehyde, where's the double bond to oxygen? At the terminus, right? At one of the ends. So this is not an aldehyde. This is a ketone. So it's propan-2-one. Very good. Sorry about that. So Any secondary alcohol can be oxidized into a ketone. And I should have mentioned that this also requires heat. In our next unit, we will learn what makes reactions favorable or unfavorable. But often, heat management is a big part of them. If it's an endothermic reaction, if it's a reaction that absorbs heat energy, then you often have to add heat. If it's an exothermic reaction, one that releases heat, then you often have to give that heat a place to go. You actually have to cool the reaction. So you'll often see in an organic chemistry lab, there's sections of the reaction that are done under heat, either over a Bunsen burner, though often with organics we avoid open flames because a lot of these things are flammable. So we have hot plates or we have heat mantles or other sort of things that can heat things up without having open flames that risk explosions. Dr. Thomas Hudlicki, who is you're not supposed to speak ill of the dead. He was a very gifted professor and also sort of famously, is it speaking ill of the dead to say a huge prick? Probably, right? But he was famously just very, very, very exacting, brutal, but he was loaded. He had patents on, in organic chemistry, you can't patent a molecule. So even if you own a drug company, you can't patent a medicine. You can't patent a drug. That patent is own the rights to something. You can't own the rights to a chemical. It's just a thing that exists in nature. But you can patent the manufacturing process. Does that make sense? So if a pharmaceutical company discovers a pharmaceutical product that has amazing effects, they have to figure out all the ways you could make that feasibly and economically, and then they have to patent all those. Because if somebody figures out a different way, then there's nothing stopping you from making that product and going. Does that make sense? So Hudlicki had patents. He's passed away since, on all kinds of things. So he was a very, very gifted chemist, and he ran a lab. And I never worked in his lab, but I knew a bunch of guys who worked in his lab, and he was famously just brutal. But I also curl with his old boss. I curl with the old chair of the whole science department for Brock University, Dr. Mercier, and he said that Hudlicki had an explosion in his lab. And they went and investigated, and they said they did all the things, and he said, well, what are we going to do to prevent this to make sure it doesn't happen again? And Hudlicki was like, it's an organic lab, it's going to happen again, and walked away. He was like, oh, okay. But you deal with a lot of things that like to explode in organics, so we try to avoid open flames. So in the presence of heat and an oxidizing agent, any secondary alcohol can be oxidized into a ketone. We'll just restate, requires heat and an oxidizing agent. I always remember that on my second year organic chemistry final, the prof was like, the first one's a real softball. And it was literally what will be the product if butane 3-ol or butane 2-ol is heated or is placed in a bath of hot potassium permanganate. And that is a softball question. You guys know the answer to that now, right? It's going to form a ketone. And I remember I was in such a fluster just being like, I don't know what hot potassium permanganate does. Oh my God. And then my friend Amanda was crying behind me, and then I got upset that she was crying behind me because I thought it was selfish to be loudly crying while everybody was stressed out. So then I was like, Amanda, shut up. She was like, and I was like, Amanda, shut up. What, you think you're the only person who finds this hard? What, nobody else is stressed out right now, just you? You're the only person in this gym? And so then we started shouting at each other, and then a proctor had to come over and tell us to be quiet. That's a true story. I got 17% on that exam. Amanda got 26. So maybe I should have been crying. Anyway, Amanda, if you're listening, I'm sorry for yelling at you for crying. Also, get a life, nerd. Okay, what about primary alcohol? Well, you should already know the answer. What are we going to get when we oxidize a primary alcohol? Let's stick with our prop theme here. We'll do propane 1-ol as a primary alcohol. And what are we going to need if we're going to oxidize this? Sorry? Yeah, we're going to need an oxidizing agent. Okay. So sometimes we'll show that just like this, which I do want you to get familiar with. That's the generic symbol for an oxidizing agent. Yeah, I was wrong. I get wrong. Yeah, I know. Do it this way. We'll change it thereafter, and then I'll be like, what are you talking about? It was never like that. God, pay attention. It doesn't matter. Often they'll write them all above. Sometimes they write one above, one below. Good question. Doesn't actually matter. As long as it's written around the arrow, we know that these are things that are not consumed in the reaction but are required for the reaction. We can write, and you can write any reaction conditions there. Like if you wanted to be very specific, if you wanted to write like 32.5 degree water bath, I mean, that wouldn't be hot enough, but you know what I mean? Like you can get quite specific here. These are the conditions of the reaction, but not the things consumed. Good question. What are we obviously going to get? Again, where's the reaction going to happen? It's going to happen here. And in an oxidation reaction, we make more bonds to oxygen. So we're going to make another bond to oxygen. That's going to form a ketone. In this case, what ketone? What do we call this? We do not call it carbon. We call it an aldehyde, so the name of this particular aldehyde would be? Propan 1 propanal. Yeah, do we need the 1? No. Why do we not need the 1? Aldehydes are always on the 1. Very good. We'll get there. Did I put an OH there? Why did I put an OH there? That would have been a carboxylic acid, but there's no O there. Sorry about that. So there we go. Yeah, sorry about that. And obviously, what has to be dealt with? Because they can't just disappear. Yeah, we have 2 H's here, and they're going to get released as H ions. Did you draw them both this time? Yeah. That's funny. I'm sorry. What's the hybridization state of carbon now? Yeah, so it's noteworthy that this changes the hybridization state of the atom involved, which means it's always going to change the shape of the molecule, right? That's true for the previous one as well. So a primary alcohol oxidizes to form an aldehyde. But aldehydes can be further oxidized and will be. In the presence of water, we could take that aldehyde we just made. So I'm going to set this as the background. I don't know why I didn't do that sooner. There we are. Now, this still requires an oxidizing agent. I picked this one this time. What's that one called again? Potassium dichromate. Good. Another classic oxidizing agent. Sorry? Sorry, one more time? Okay, could you stop wasting my time? You know, like, time is precious. I don't know if you've noticed this. I'm always focused. We're always on point. I don't waste your time willy-nilly. Are you okay? Do you want me to go get you a water? You're okay? Okay, don't die. I haven't lost anyone yet, and I really would hate for you to be the first, or anyone for that matter. Okay, in this case, a further oxidation we can get will take place with this attack here, right? And again, we're going to get what? No. In fact, we're going to get those H plus ions again. Oxidation reactions tend to result in getting these H plus ions forming. But what are we going to get? What's going to end up on the chain here? Yeah, we're going to get that OH group on. In fact, I should have. If I'm sticking with my kind of convention here. Not a carbonic acid, by the way, a carboxylic acid. So in this case, what was this one called again? Propanal, right? Reacts with water in the presence of an oxidizing agent. Any oxidizing agent will do to form, what is this? Propanoic acid. Good. So aldehydes oxidize into carboxylic acids. This also means that oxidation is a poor way to produce an aldehyde because the aldehyde will further oxidize. Does that make sense? So if you wanted to make an aldehyde, if you were going to just oxidize, if you're thinking, oh, I'll just add some potassium permanganate and some heat, that will produce an aldehyde, but then it will also produce a carboxylic acid. There are ways you could prevent that from happening. And we'll talk about that in our next unit when we talk, or 2 units from now, sorry, when we talk about how you sort of control the outcomes of reactions. But for now, enough to know that if you oxidize a primary alcohol, you'll get an aldehyde. But then that aldehyde can also be oxidized further. Sorry? I've given you some questions here, and oh shoot, did I copy and paste the wrong questions in? One sec. Oh, for goodness sakes, guys, this is the wrong homework. I pasted the wrong homework in here. This is tomorrow's homework. Oh no. Shoot. Kate, after all that work, I had you staple the wrong homework onto these sheets. I'm sorry. That's my fault. Oh, shoot. I will put some homework up here right now. I am so sorry, guys. That's a... Darn it. Oh, guys, I'm such a failure.
I was going to say, I don't work.
You don't even recognize that name. No. Yeah, no, you're not there yet. I'm so sorry about that. SCH4U, oxidation reactions, worksheet. PDF. Oh, that's so annoying, guys. I'm sorry. No, not redox. Organic. We'll say oxidation of alcohols. Yeah. Amazing. Thank you so much.
Just because I was trying to get intentional and just every question.
Oh, you know what it's time for? No, it's time for it. Take on with me. Guys, even if the bell rings, just give me a minute. Okay, don't disappear.
Okay.
Oh no, take care. Go. Someone else come with me. Hang on. Come on.
Sorry. Okay, send. You got right? You're not bad. I need to tell her who didn't show up on Friday, and I need to excuse this because I absolutely. Yeah, I'm so bad. Oh, we had so
So if you want to find some mass, it's carbon in waves.
and then we try to get volunteers to like make one.
You have 12 carbons made from times 12.0
Oh wait.
plus 26 plus 26 hydrogen. More mass of that. And more mass of carbon.
Oh, next to a minute.
Plus
Okay, I have two. I have 27. Here.
yes.
Also, you're definitely not midlife. I am past midlife. You are not midlife. Okay.
It feels like life. Yeah.
Guys, can we grab a textbook? Listen, did I want to get nicer, newer textbooks that you guys could use? Yes. But here's the deal. What I need you to do is write your name on the board and the number you have. I will put it into a spreadsheet later. Quiet. This, by the way, is actually a very good
Just a reminder that tickets are being sold in the front way for the Halloween dance. We'll see you there.
Oh, it's anyone on the board? Or you said like the volleyball? I don't know about that. Yeah.
Turkey breast stew for $2. Our salad is Caesar salad for $4. Our entrees are lamb and pasta with a for $5. Our pizza for $2. Chicken pizza for $3. And remember, you can always have our card. $4 for $4. We have a little cake for $1 each. Bacon deck, where there you go.
A0254.
Are they all A2?
You tell her.
And can you make that tight, please? I'm never doing anything for you like that. Thank you. Never doing anything for you. Yeah, that looks
Can I tell you something? You say that, but I have heard numerous people say that you seem very organized and on the ball. So you know what? Even if they're wrong, just run with it.
Fake it till you make it.
Yeah.
Some people think I'm faking it well. There's a way of faking it. By the way, have you guys seen? I can't find my section.
Guys, tomorrow we're going to jump in and do a little lab. Just a little one. It's not going to be a big one with a write-up or anything, but we are going to be in the lab, which means I'd like you dressed appropriately for the lab. Make sure you got a hair tie. Make sure you're wearing closed-toed shoes. Not a good day to wear big baggy things. Not a good day for like bathrobe day. And make sure that your safety stuff is all done, obviously. No food in the lab tomorrow? Yes, I can help you with that. I've got to run to the, are you going to play some music at lunch? Sure you are. Yeah, sure you are.
I was already doing just bomb donuts.
Oh, you're amazing. Oh, you're amazing. Yeah, exactly right. So once you get those, this is actually easy. This is the hard part. This, don't worry about it. Just get that done, and then I will show you this. That's awesome. Good for you.
What?
Where?
Like,
Do you mind grabbing the cajon?
this
Yeah. Is that okay? Yeah.
on that shelf. Like,
Hi, Everingham. How you doing?
right in there.